Hello everyone. We were studying this chapter on threads and we discussed in our introduction to thread that a thread is a separate independent execution within the same program. Right? In our normal programs, there's only one execution, so therefore only one thread. But in a multi-thread program, you can have multiple executions that are independent of each other and that can run in parallel. And all these execution will each call each of them a thread, and each of them will have their own stack within the program. Okay, they're part of the same program. They share the global data, they share the heap, they share all the code of the same program, but they do not share stacks. Stacks are different for each thread. So then we saw an example of running threads in parallel, and then we saw another example where threads are sharing this global data. This global variable counter will be shared between all threads in this program. And within a thread, basically this is a function that we would run as a thread multiple times in parallel independently. And all these threads running the same function would access this variable counter, and they all will try to increment this counter like 10 million times. Okay, so 10 million times this loop will run, and in each iteration they will increment the value of the counter by 1. Okay. So multiple threads would be doing this operation in parallel. They will be accessing the counter in parallel and incrementing its value, trying to increment its value 10 million times in parallel. So this was our thread function. You can see that it only prints the begin and end message done. And then within these two prints, it is running this loop 10 million times and increment this value of counter. In our main thread, we basically create two threads. In main function, we create two threads and we store the data of these two threads in P1 and P2. And both these threads will be running this function myThread, which we saw in the last slide. Okay, so this function is basically accessing that global variable counter and increment the value 10 million times, but this will be happening in two threads running in parallel. And A and B are the arguments that we are passing to these two threads, which they will print just to identify themselves. So after these functions are completed, like pthread create P1 and P2, both those threads are created and they would start running in parallel, and they would basically increment the counter in parallel 10 million times, both of them. So here at the end of main, we are calling pthread join to wait for those two threads that we just created to terminate. And then here we are printing the value of the counter. So if both the threads, they are running in parallel and they are incrementing the value of counter 10 million times, so each of them will increment the counter 10 million times, and we would expect that here, once both those threads are terminated, main will print the value of counter and it should be equal to 20 million. Okay, because both the threads, they incremented the value of counter by 10 million. But when we ran this program last time, we saw that the value of the counter printed here at the end is not necessarily 20 million. So from now in this lecture, we'll continue from here where we left off last time, and we'll investigate why this value of counter is not being printed 20 million. Okay. So the basic problem is that when threads share data and they operate on data in parallel, on shared global data, when multiple threads, they operate in parallel on shared global data, then certain problems can arise, and we'll see what are those problems and how we can control them. So we saw a code last time and we saw that the value was not being printed 20 million times. So the reason for this is that this, if I go back and show you this instruction, counter is equal to counter plus 1. So this is one instruction in C code. But when it is translated to assembly and ran at low level in the processor, we will see that this instruction is not one instruction. Okay, so counter is equal to counter plus 1 translates into 3 assembly instructions. So here it's the assembly code for Intel processors, and we can see that, let's say this value counter is stored in RAM at this address 0x8049A1C. So this is the address of the variable counter in RAM, and the 3 instructions that will constitute counter plus 1 are composed of First is the load instruction. Okay, load, basically we will load the old value of the counter from the RAM into a register. Okay, so since this is the address of the counter variable in RAM, so this move instruction, it will go access this address where the value of counter is stored and load that value into this register EAX. Okay, so this is the equivalent of load instruction, move from RAM to register. The value of counter, let's say it's 5, the value stored in counter right now. So that value will be loaded from this address in RAM and stored into the register EAX. So the register EAX now contains 5. Next is the increment part. So add instruction would basically add 1 into this value stored in EAX, which was the value of the counter, and store the result again in EAX. Okay, so here the EAX register here is operating both as the source register for add and also for the destination register for the result of the add. So the value in previous value in EAX was 5. So add register would basically add 5 to 1 and store the result, which will be equal to 6 again in EAX. So now the value of counter has been incremented, but still it is incremented only in the register. The value of the counter in RAM is still the old value 5. It has not yet been incremented. So this final instruction, which we'll call store instruction, it would basically move the updated value of the register from this register, updated value of the counter from this register EAX into its location in RAM. Okay, so updated value of counter in EAX is 6. So this move register, it will basically move this value 6 from register EAX to this address where the variable counter is stored in RAM. Okay, so after the completion of third instruction, the value of the counter in RAM will be updated and it will become 6. So the instruction counter is equal to counter plus 1, which was 1 instruction in C, has been transformed into 3 instructions in assembly. So if this thing is happening in multiple threads in parallel, what can go wrong? What can go wrong? So assume we have a single core processor and both these threads are trying to run on the same single core processor, and that single core processor can only run one thread at a time. So let's say thread T1 is running and it is incrementing the value of counter. All these assembly instructions are executing, and let's say at any given moment the value of counter is, let's say 115. So at 115, this counter is equal to counter plus 1 instruction is being executed in thread T1, and it basically loads the value 115 from RAM into register EAX. Now let's say, okay, 115 comes in EAX and then it increments it 115 plus 1 and EAX becomes 116. And at this particular moment, before the thread has a chance to store the value of register EAX into counter in RAM, a context switch happens. Right? And context switches are managed by the scheduler and they are not in your control, so they could happen anytime. So let's say context switch happens after instruction this 105 and before 108. Okay. So after the value of counter has been incremented, let's say to 116, but before it has been stored to RAM, a context switch happens. Thread T1 context is stored in RAM and thread 2 is loaded and its context is loaded in the processor and starts executing. Let's say thread T2 is also going to run the same code and it will be calling counter is equal to counter plus 1. So these 3 same instructions would be executed in thread T2 also. So now let's say, remember that thread T1 has not yet had the chance to update the value of counter. So the value of counter in RAM is still 115. So let's say thread T2 runs, it loads the value of counter from RAM into register EAX. It receives 115 in EAX, it increments it, it becomes 116, and then it stores the value 116 into RAM. Okay? And thread T2 continues executing, and let's say after a long time, when the counter has reached, let's say 5 lakh value, it gets switched. it gets switched to, the context gets switched, and the context of T2 is stored in RAM, and the context of T1, the old thread, is loaded in the processor again. Now thread T1 will start its execution right where it left off. Okay, so if you remember, it left off here. It had the value 116 in register EAX, and it was going to store this value in RAM, but has not done it yet. Okay, so it will start by executing this instruction on address 108, and it will store that value 116 in RAM. Okay? But the value in RAM has been updated by thread T2 to 5 lakh. Okay? But thread T1 does not know this. So it will simply carry on with its execution, and it will overwrite that value 5 lakh by this value 116. Okay, so all that increments that have been done by thread T2, they are lost now. Okay, all that work done by thread T2 has been wasted, and thread T1 has basically overwritten the value of counter with value 116. Okay, similarly, when both threads continue running, this kind of context switches happen, and they will be overwriting the value of each other all the time. Therefore, the value that we receive at the end is almost never equal to 20 million. Okay. And all this because these threads are accessing shared data, and they are accessing it without any synchronization. By synchronization, I mean that context switch is not in our control, and at any given moment, the scheduler can deschedule one thread and schedule another thread, and situations can arise like the one we saw right now, and the threads can overwrite the value of each other, and therefore the value is not incremented in an orderly fashion like we expect it to by looking at the C code. Okay, so this again, one of the reasons is because shared data is being accessed, and shared data is being accessed in parallel, and context switching is not in our control. We'll see in the next chapter how we could improve this to write correct code, but for the moment we are going to do some digging and make some concepts clear by defining some definitions. So here this is the same execution that we saw. The count value of counter is 50, so one thread loads the counter value 50, increments it to 51, and before it could store, it gets context switch. Okay, and interrupt arrives and context is switched and T2 runs. So since the value of counter is still 50 in RAM, so T2 will also load 50, it will increment and it will store 51 in RAM. And at that moment, we see that another interrupt comes and context is again switched. T2 resumes its, T1 resumes its execution and starts from this instruction where it was going to store the value of 51 here. It had incremented, but it had not yet stored. So it will continue after that and store the value 51 in RAM. Okay. So here we can see that the origin value of the counter was 50. Counter was incremented 2 times, once by thread 1 and the second time by thread T2. But after 2 increments, the final value of counter is 51 instead of 52. But after 2 increments, you would expect the counter to be 52, but the counter is 51. Okay. Why? Because thread T1 overwrote the value incremented by thread T2. So any combination of these schedulings can happen, and the takeaway here is that since scheduling is not our control and not in our control, we cannot predict what will be the final value of the counter. So this, since we cannot predict what will be the final value of our counter, this makes in our program indeterminate. Indeterminate means we cannot determine in advance what will be the result of our program. Imagine if all your programs are like this. Anything can happen at any time, and you are never sure what your program will do next. Okay, so this is a very dangerous situation. If we have a program whose execution is indeterminate, we do not know what will be the result, that program is almost useless for us. Okay? And we do not know the result or what the program will do, because the result of the program depends on the sequence in which the instructions are scheduled. Okay, so the sequence of scheduling is not in our control. Instructions are scheduled based on the scheduling decisions taken by the scheduler. Okay, the scheduler will decide when a thread should be descheduled and when another thread should be run. Okay. So depending on the sequence or the scheduling order, the result of the program can be anything. Okay. If we go back to this slide, if the sequence order was different and this move instruction happened before the context switch, then thread T1 would have stored the value 51 in RAM, and thread T2 would have read the value 51 and incremented the value to 52. Okay, the final result then will be 52, which will be correct. But that would happen only if this move instruction would be scheduled before the context switch here. But that, as we just discussed, is not in our control. Okay, so if the result of the program depends on the order of execution of instructions or in order in which they are sequenced, which is not in our control, so that kind of program is indeterminate. Okay, and an indeterminate program is useless or dangerous for us. So to see how computer science deals with this indeterminacy, we'll first define some definition. Okay? The first definition here is critical section. Critical section basically is a portion of code which, if executed by multiple threads, can result in a race condition. Okay? So what is a race condition? A race condition is a condition of indeterminate behavior in our program. And again, when there's a race condition in our program, then our program of our the behavior of a program is indeterminate, and it depends on the sequence of scheduling of these instructions. So this is called a race condition, and race condition basically makes our program indeterminate, which means the output of the program is never sure what will be the output of the program. So the portion of code which, if executed by multiple threads, can result in race condition, that portion of code is called critical section. Okay. Now, if I ask you what will be the critical section in this code that we saw, this was a thread function and this is a main function. So what will be the part of code which, when run in multiple threads, would make our program indeterminate or would cause a race condition in our program? So if you have guessed it, then you will know that this part of the program, counter is equal to counter plus 1, this part is accessing global data. Okay? And if it is run in multiple threads in parallel, it would cause race condition in our program. It would cause the behavior of our program to be indeterminate, okay? Just like we saw in our examples. So this part of our program is critical section for our program. Okay? So again, the critical section is part of the code, the portion of code which, when executed by multiple threads in parallel, can result in race conditions. So usually one of the signs of the critical section is that it is accessing a shared resource. It is accessing shared data. For example, here in our example, the shared resource was the location of the variable counter in RAM. Okay, so variable counter was the shared resource that both the threads were accessing in parallel. Okay, it was a global variable, so it was accessible to all the threads. So it can, they can modify it while running in parallel. Okay, so they are accessing a shared resource in the critical section. So to ensure determinate behavior in our program, to avoid indeterminate behavior in our program, we should make sure that critical sections of our program are not executed concurrently. Okay? By concurrently means in parallel. That could be on a single core processor or on a multi-core processor. At any given instance, only one thread should be executing the code in the critical section. Okay? So this principle, in which only one thread will execute the code of critical section, we call it mutual exclusion. Okay, so they mutually exclude each other from critical section. Only one thread is in the critical section executing the code of critical section at any given time. All the other threads are excluded from the critical section. Okay, so this principle is mutual exclusion. So this will solve the problem of race condition as we saw in this slide. If right now you see here T1 is in critical section, counter is equal to counter plus 1 is the critical section of our code. So counter is equal to counter plus 1 is basically these three instructions: move, add, and move. So thread T1 is in its critical section, and before thread T1 finishes its critical section, thread T2 starts its critical section. Okay, so at this given moment, at this moment in time, thread T1 has not left the critical section yet. It is still in the critical section, and T2 also enters the critical section. So here both threads T1 and T2, they are in critical section, executing the code of critical section concurrently. Okay. So this is violating the principle of mutual exclusion. So if we move this instruction up, okay, so that thread 1 finishes its critical section, and only after thread 1 has finished its critical section, then thread T2 enters the critical section, then we will be implementing mutual exclusion. Only one thread would be in critical section at any given time, and this would basically result in correctly updating the value of counter. Okay, and race condition would be avoided. So again, to avoid race conditions, we should make sure that critical sections of a program are not executed concurrently. They are they are not executed concurrently. They should be executed in a mutually exclusive fashion, in the sense that only one thread should be in the critical section at any given time. So that way we can avoid race condition and indeterminate behavior in a program. So another definition is that of atomicity. Atomicity basically means atomic operations are either executed in full or they are not executed at all. So they should not be, they cannot be executed in half, like half of the operation has been done and half of operation has not been done. Okay? So this is not possible in atomic operations. So to achieve mutual exclusion, we should make sure that our critical sections are executed atomically. Okay? By this we mean that, let's say this is three instructions are critical section. Counter is equal to counter plus 1 are these three instructions. So they should be executed atomically. Atomically means either they should be executed together, a set of three, or they should not be executed at all. It should not happen that only two of these instructions are executed, and before the third instruction gets executed, some other thread also enters the critical section. Okay, so critical section should be executed atomically. Thread T2 should enter its critical section and only after thread T1 has finished its critical section. So critical sections should be executed atomically in an all or nothing fashion. So if they are executed atomically, then we can make sure that only one thread is in the critical section at any given time, and we can achieve mutual exclusion. So threads need to synchronize with each other to access global data, shared data, as we saw in the last slide. Sometimes threads also need to wait for each other. They need a synchronization in a way that one thread is waiting for another thread to finish a job, and it can only continue its execution after that thread has finished its job. Okay? So again, we can in this chapter we will study both these kind of synchronizations. The first one is how do threads synchronize among each other to access shared global data, and secondly, how do threads synchronize to wait for each other. Okay? So in the next few chapters, we will see how the operating system facilitates these two kind of synchronization between threads. So here it's just a historical insight that operating system was one of the first concurrent programs, which means multiple critical sections in the operating system could run concurrently. Okay, so multiple processes can run, and these processes execute the code of operating systems. So it can happen that multiple processes are executing the same code of the operating system concurrently. One process, while executing the code, gets interrupted, another process runs, and it executes the same code operating system. Okay? So again, it is executing the same code of operating system concurrently, and those codes of operating system, they can access global variables which are shared between processes, the OS data structures which are global and shared between processes, and they can manipulate or modify these structures using the same critical code concurrently, which would basically result in the same kind of problems that we saw when we access the variable counter through multiple variables through multiple threads in parallel. Okay? So because of the interrupts, one process can get interrupted and another process can get run, and it can run the same code accessing the same global data structures of the operating system. Okay, so operating system was one of the first programs that had to deal with race conditions and concurrency. So the makers of operating system, they came up with multiple methods to solve this concurrency or indeterminate behavior or race condition problem, and we will see how they were able to achieve mutual exclusion and atomicity in the next few chapters. Okay. So this is all for this chapter. And in the next chapter in the book is basically thread API. Thread API basically is talking about the functions used to create a thread, like pthread create, and then the function used to wait for a thread, okay, like pthread join. And using these two functions, you can create threads, pass values to a thread when it is created, and return a result from a thread when a thread finishes. Okay? So the example of pthread create and passing value to a thread, we saw it in our last lecture, and we also saw an example of pthread join, how you can use pthread join to wait for a thread that your program created for its termination, and then once that thread is terminated, pthread join will return and you can continue your execution afterwards. Okay? One thing that is extra in this chapter is that you can use pthread join to get a return value from the thread. Okay? So that chapter, since we've already discussed almost 90% of it in the last chapter, you are encouraged to read on your own and use that API to create threads, pass values to a thread, and return values from a thread in your own program. Okay, we'll continue after that chapter in our next lecture. Thank you very much.